This is an introductory tutorial for SimXpert. The purpose of this tutorial is to introduce you to the SimXpert environment and teach you the basic functions of SimXpert. In this tutorial, you will learn how to model a cantilever plate, how to mesh the cantilever plate, how to constrain the cantilever plate and apply a load, how to analyze a cantilever plate and view the results. In SimXpert, one can select different workspaces and different types of simulations. We will be working in the structures workspace. It is very important to check if your desired units will be used before you start. If you want to change your units, go to the Tools menu and select Options. Highlight the Units Manager and click on Standard Units. Scroll down to select the SI units. In SimXpert, one can import geometry previously created in a CAD package by scrolling down to the Import option and selecting the file type. In this tutorial, we will model a cantilever plate using the geometry tools in SimXpert. Under the Geometry tab, select Planar in the Surface group. Use the one-point method and enter the midpoint as 0, 0, 0. Make sure that the XY plane is selected. Enter the dimensions of the plate, a length of 1 meter and a width of 0.1 meters. Make sure the length and width is in the correct direction by clicking the Preview option. Click OK. Click the Fill button on your View Manipulation toolbar to view the model, or press the F button on your keyboard. To assign model properties, click on the Materials and Properties tab and select Isotropic under the Materials group. Rename the property as steel. Enter a Young's modulus of 200 gigapascals and a Poisson's ratio of 0.3. Density is only required when taking mass into account. These are the only required properties for a linear static analysis. Notice the steel properties placed in the model browser on your left. Since we are using a 2D element, select the shell property in the 2D group. Rename the property as desired. One can associate the properties to the element, the surface, or the whole part. If you assign a property to a surface, all the elements on that surface will have that specific property. The same goes for parts. We will assign a property to the surface. To do this, click in the Entities box and select the surface in the graphic window. Click in the Materials box and select the steel property in the model browser. Enter a part thickness of 10 mm, but remember the units are in meters. Under the Meshing option, create a surface mesh for a 2D model by clicking on Surface in the Auto Mesh section. Click on the surface of the model in the graphics window. If the Calculate option is ticked, SimXpert will automatically select the mesh size. This can be overwritten by entering a new value. We will now be using a mesh size of 10 mm. The default element and mesh type is sufficient and will be used. We can delete the mesh in the Auto Mesh section and remesh the model if the mesh size is incorrect. Right-click on the shell properties and select Statistics to view the information about the property and to also verify the number of elements to which the property is assigned. Clicking on the Hide All Geometry in the Entity Display filter will allow you to see the mesh. Clicking on the Show Surface Geometry icon will allow you to select the surface present in the model. The same rule applies to solid geometry, curve and line geometry, and point geometry. You can also hide or show the finite element entities by selecting or deselecting the 2D finite elements. You can move the model by holding in the Shift key, clicking on the middle mouse button and dragging the mouse. You can zoom in and out by holding down the control key, clicking the middle mouse button and dragging the mouse up or down, or by scrolling with the middle mouse button. To rotate the model, hold down the middle mouse button and rotate the model as desired. Press Shift and I together on the keyboard to show the isometric view, and press F to view the whole model. If you are not comfortable with this method, you may also use a view manipulation toolbar. You can also use the render tool to render the finite elements. We will now apply load and boundary conditions. Click on the Load and Boundary Condition tab, LBCs, in the ribbon toolbar. Select General Constraints and click in the Entities box. Zoom to the one end of the surface. Picking filters will appear whenever you hold the cursor over the Entities box or when you click in the Entities box. The picking filters may also be accessed in the Picking Filters toolbar. In the Picking Filters, deselect the Sheet features, Surfaces, Nodes, Wire features. Leave curves selected and deselect point features and points. This will allow you to only select curves or edges. Now click on the edge of the plate to select the curve. These options here are constraints. The tick next to the TX means that the nodes on the curve or edge you have selected won't be able to translate in the X direction. Removing the tick will no longer constrain the nodes on that curve from moving in the X direction, and the model will be able to translate in that direction. The tick next to the RX means that the nodes in the curve won't be able to rotate about the X-axis. Removing the tick will allow the model to rotate about the X-axis. For a cantilever beam, all 6 degrees of freedom should be restrained. In the Render toolbar, turn on the Detailed Rendering to see the constraints. Move to the other side of the plate. Under the Load and Boundary Conditions tab, select Force in the Loads group. In the Picking Filter, select a node at the corner of the plate and enter a magnitude of 100 newtons in the Scale Factor box. Pick a negative Z direction and make sure the direction of the applied force is correct. The loads and constraints can be shown or hidden by clicking Loads and Boundaries. The cantilever plate has now successfully been constrained with an applied load. In order to solve the model, we will now need to create an MD Nastran job by right-clicking on the file set and creating a new Nastran job. Give it a job name and select solution type, in this case linear static analysis. Create a solver input file path and click Save and OK. Notice a simulation created in the model browser. Right-click cantilever plate under Simulations and select Run. Navigate to the solver input folder you have created with the new Nastran job. In here you will find a PDF file, which is the MD Nastran input file created by SimXpert and contains the model definition. The .xdb file is a results file used in SimXpert for post-processing. The .fo6 file is a results file and is the main Nastran output file. It contains the results and also shows error messages. To check whether Nastran has finished solving, open the .fo6 file and scroll down to the bottom. If the end of job phrase is present, it means that Nastran has finished the solving process. If it is not present, search for fatal by holding down the control key and pressing F for find. In this case, there were no such errors. In SimXpert, click on the File menu and click Attach Results. Click in the folder icon and navigate to the solver input folder previously created and select the .xdb file. Under the Results tab in the Tools ribbon, select Deformation. Highlight Static Subcase in the Result Cases window. Select Translational Displacement and click Update. Click Deformation in the Plot Property Editor. Tick the Show Undeformed option and click Update. This will allow you to see the undeformed model and compare it with the deformed model. You can also change between true and scale deformation under the deformed scaling option. To save the image, click File and select Print Setup. Set up Print to File and navigate to the desired folder where you want the image to be saved. Name the file and select Save. Click on the File menu again and select Print. This saves the image in the folder just created. Navigate to the folder just created to find the image that results ready to be used. In SimXpert, click on the Results tab and select French. Highlight the static subcase. Select Stress Tensor and von Mises as derivation. Also highlight both layers. Z1 is the top layer and Z2 is the bottom layer. Use Maximum Plot and click Update. This shows a von Mises stress on every element at the upper or lower surface of the plate. Under the File menu, click on Detached Results. Highlight the .xdb file and click OK. The .xdb file has to be detached before you can rerun the analysis. This concludes the introductory tutorial. This tutorial was brought to you by STech, engineering technology for better business.